way to make them more understandable. So this was the problem I was working at when I came to MIT. And in that first fall in 1972, when I was first on the faculty at MIT, sometime in the middle of that fall, I had this wonderful moment in which I suddenly saw the solution. And the solution was to is to connect this idea of a multi-operation module to abstract data types. And the connection is kind of clear in retrospect, because if you think about a data type, it has a bunch of operations, and inside it has a state. And the operation implementations manipulate the state, but from the point of view of the user, you don't see that state. What you see is this indirect use of the state. And this was already clear in the programming languages that existed at the time, because everybody used arrays. But under the covers, of course, there was a complex implementation of arrays going on. You know, so in retrospect, so why did I get this idea? This is, of course, one of these mystery questions, and I can't tell you the answer, but I can tell you a few things. The first thing is, the idea was waiting to be discovered. Because when you look back at the literature, you see it sort of on these, it's sort of like on the surface of these papers, it's just that nobody had quite put it together. And in fact, you know, more than one person gets an idea like this at about the same time when an idea is ready to be discovered. The other thing is, I was really working on the problem. I mean, I was thinking about this problem all the time. You don't get an idea like this just by luck. You get this idea because you are focused on the problem, and then you are in a position, if you're lucky enough, to see that here's a solution to that problem. Now, I don't actually believe in working all the time. In fact, I am a person, I come into work in the morning, I work until I go home at night, and that's, like an 8 or 9 hour day. And then I put my work aside, and I typically don't work at night. I don't work on weekends. I mean, sometimes I violate this rule because there's a conference coming up and I have to get a paper out, but generally that is my work schedule. And I recommend this, because what I have always found is the time when I'm not working is also extremely valuable, actually, for getting my ideas together. And a very common pattern that I have had throughout my career is in the morning when I drive into work, I spend that time thinking about what I'm going to do during the day. And what problems will I work on today? What do I have to accomplish today? And I often find that I have an idea about how to solve a problem in the morning that I didn't know how to solve the day before. So my unconscious mind is working on these problems when I'm not really working on them, and this has been a very valuable paradigm. The other point, of course, is if you get exhausted, you can't really do anything very interesting. Okay, now the next thing that was interesting that happened in 1972-73, in that first year at MIT, was that in the spring of 1973, there was this very interesting meeting held in Savannah, Georgia, and this was a joint ACM, SIGPlan, SIGOPS interface meeting. So SIGPlan is the programming languages community. SIGOPS is the operating system community. This was a joint conference between the two communities, ostensibly to look at the question of what kind of programming language do you want in order to build operating systems? A really phenomenally boring question, if you think about it. Because there are very few operating systems. There are a gazillion applications. The interesting question in programming languages is, what programming languages do I want to support the gazillion of applications? Of course, at the time, operating systems were a very challenging topic, so you can understand why this was happening. However, in reality, that conference wasn't about this topic at all. It was actually about programming methodology. And I gave a talk on my ideas about abstract data types, and Steve Zillis, who was a graduate student at MIT at the time, had written a little working paper for that conference on similar ideas, and so Steve and I started to work together. And so Steve and I together were the people who put together the real notion of abstract data types. Steve was a great person for me to work with because he was a mature graduate student. He actually was an employee of IBM. He was older. He was working for IBM full-time, but they gave him as much time as he needed to work on his thesis. He came in with all the knowledge of the IBM languages, and IBM was the predominant producer of programming languages at that point in time. I, of course, had my AI background. I knew Lisp. And between the two of us, we pretty much covered the field and what was available in programming languages at the time. And by making that connection from partitions to abstract data types, I was moving into the programming language domain. So I was starting to do work in programming languages. And so, of course, what Steve and I did was we read the literature. Next slide. Oh, here we go. Okay. So I'm going to tell you a little bit about some of the papers we looked at. Again, I'm not showing you everything. I'm just showing you a few, and I'm not trying to make a statement that the other ones aren't interesting. It's just I can't talk about them all. So here's the first couple of papers that are interesting to think about, and these are papers on what was called extensible languages. So what was going on at the time was people were very worried about whether there was such a thing as a universal programming language. Could there be a programming language in which you could write any application you wanted to? I mean, this is another one of these questions where we look at it today and say, huh? You know, of course there is, because we use them all the time. There's C, there's Java, you know, you name it. You can write whatever program you want in whatever programming language you want. But at the time, it was less clear that this was actually true. And the fact is that programming languages remove expressive power. As you move up from a low-level thing to a high-level thing, you lose access to the features of the low-level things, like the go-to statements. And you have to replace them with whatever it is the programming language makes available to you. And the worry was, maybe I wouldn't be able to do what I wanted to do because it took something really important away. So people were worried about that problem, and that was what the basis for this work on extensible languages was. Now, in that first paper by Steve Schumann and Pierre Girand, what they were doing was, this was a summary paper talking about what was going on in this field at that particular moment in time. And they said there are actually two types of work going on in extensible languages, syntactic and semantic. Syntactic, there was a bunch of work that had to do with allowing users to change the syntax of the programming language. This is actually a really bad idea. And the reason it's a really bad idea is because, as we know today, although it was not clear then, reading programs is more important than writing them. Because a program is written once and then read many times. I'm talking about programs that are used in systems that last for some period of time. You yourself may go back and read your own program a year from now. More likely some poor soul who isn't you has to read and maintain your program. And what you want when you have to understand somebody else's program by reading it is at least a syntax you understand, so that you can get the basic idea of what that program is doing. And if the person could have redefined the syntax, this is not such a great idea. But they also talked about what they referred to as semantic extensions. This has a little more potential. And an example of the kind of work is this Bob Balzer's thesis, very early work, in which he said all data types have 4 operations. So he's thinking about there are the built-in data types, but maybe there's more data types that users can define. So that's the notion of a semantic extension. So he says all data types have 4 operations. So what he's really doing is he's thinking of data types as collections, and there's an operation to create the collection, insert into the collection, remove from the collection, access the collection. And every data type is going to have operations like that. And he had a little bit of syntax to allow you to define those operations. So this was a step. But there were 2 things lacking that made it not data abstraction. First of all, it had no encapsulation. So it was just a surface mechanism, like a type definition in some sense. And the second problem, of course, is that no, it's not true that all data types are collections. There are many data types that are not collections at all. And so this is only going to be able to capture a small subset of the data types that are really going to exist. This is an early paper on Simula 67, a very interesting and influential language. And this was interesting to us. Simula 67 was the underpinning of object-oriented programming. It was the language that introduced the notion of classes and subclasses. So if you look at the way that that research developed, it all came from Simula 67. And these classes are data type-like in the sense that you can define many procedures inside a class and they have some state that they can access. At that point in time, however, there was no encapsulation in Simula 67. And Steve and I also believed that the notion of subclassing was not going to help us get to the notion of abstract data types. And so we read these papers, we knew them, we essentially put them aside and didn't think about them any further. By the way, this paper was in a very influential book. We refer to it as the Little Black Book. It had 3 monographs in it, this one on Simula 67, a paper by Dijkstra on top-down design, and a paper by Tony Hoare on data structures and reasoning about data structures. So these are very important papers and a very interesting book. This is a very interesting paper by Jim Morris Jim was interested in, it's sort of a follow-on to Parnas's work. So the question is, how do you do this modular reasoning anyway? Parnas said you have to know the interfaces. Jim was interested in the question of what rules do you need about the way modules are used to enable local reasoning. And what he said, what he did in this paper is he pulled out the rules that we understand today. He said, outside the module, you should not be able to modify the data structures that are hidden inside the module. He also said, outside the module, you shouldn't even be able to look at those data structures. And the reason that's important is, the first one's fundamental for reasoning. Because if some code on the outside can get inside and muck around with the data structures, then you can't reason about that module independently of the millions of lines of code on the outside. The second one is important for modifiability. Another virtue of modularity is that if you decide this module isn't implemented efficiently enough, well, that's okay. You just rip it out, replace it with another one that implements the same interface, maybe using very different data structures, and the rest of the program is not affected by that change. But of course, if the rest of the program could see those original data structures, you won't be able to do that. So Jim was able to elucidate these very fundamental principles about what modularity is all about. Then he went on to ask the question, well, how do we enforce this? And he came up with an idea that was fundamentally like encryption. He said, well, what we do is there's a key associated with each module that's only the module knows. Every time an object goes out, you encrypt it. And then when it comes in, you decrypt it, and that way nobody can modify it, or if they did, they can't see it, they can't modify it. If they did modify it, you'd notice it was corrupted. Okay, he never proposed how to implement seal and unseal. Of course, you could never do this using encryption, it'd be much too expensive. But at least he showed a path. Okay, and then finally this paper by Bill Wolf and Mary Shaw, another group working on abstract data types at the time, that basically said the same thing I already talked about when I talked about partitions. It's not good to have programs that communicate through local variables. It's interesting to think, though, about the state of the art at the time, because at the time, ALGOL-like languages were in the ascendant in the academic community. And these are languages that fundamentally make a big point about global variables, because they have the notion that there's an outer block with a bunch of variables, and then there's an inner block, and inside the inner block you have some hidden stuff, but you can certainly access the outer stuff. So in some sense, the whole academic community was on the wrong track, because they had a programming style that was based on sharing of global variables. So it's interesting to see how the field develops over time. Okay, so Steve and I read these papers, we read a whole bunch of others, and my memory of the summer of 1973 is that it never rained in Cambridge, Massachusetts, because Steve and I used to meet outside for lunch every day in this lovely courtyard that we had outside my building at the time. Of course, this is totally false because it does rain in Cambridge, Massachusetts, so it couldn't have been like that. But our working pattern was we would meet for lunch every day. We would talk about whatever we were working on at the time, and then we would separate, work independently, and meet again the next day for lunch. And by the end of that summer, we had pinned down what we thought abstract data types were all about. We wrote them up and submitted it to this conference, and it was published, the paper was published the following spring. And here's what was in that paper. First of all, it said, here's this idea of abstract data types. It's very important for supporting modularity. And here's what an abstract data type is. It's both a set of operations and a set of objects, where the fundamental rule is that you can only manipulate the objects by calling the operations. Okay. In addition, the paper also proposed this sort of framework for a programming language that might support this idea. So it said, in addition, we have an idea of something we call clusters as a way of implementing abstract data types with encapsulation. And we want polymorphism, or generics as they're called today. In other words, we not enough to have a set of integers, you want a set of arbitrary type. We hoped for static type checking. We said if we can't get there, we can use Jim Morris's seal and unseal. And the reason we were worried about that was because of the polymorphism. If we hadn't had polymorphism, it wouldn't have been an issue. And we also said, by the way, you should have an exception handling mechanism. Here's a surprise, that wasn't common in those days. Okay, so what I'm going to do next is I'm going to tell you a little bit about the design of Clue. So what happened was Steve and I had said, here's the way we should go. And then as a natural next step, I designed a programming language. And I'll tell you a little bit about my motivation in a minute, because it wasn't in fact just I did it. I actually stopped and thought about, is this the right next step to do? Okay, so here's what happened in the fall of 1973. 3 first-year graduate students came and said they wanted to work with me. And their names are on the slide: Russ Atkinson, Craig Shafford, and Alan Snyder. And they, together with me, were the designers of Clue. At that point, Steve was more of an interested observer. He was working on his PhD thesis, which was on algebraic specifications for abstract data types, but he was not one of the primary designers. So I actually designed Clue with 3 undergraduate students, and they started off as first-year graduate students, and we worked through the project together. I would love to show you a picture of them, but I couldn't find one. There's a picture of me in about 1974. And the person I'm talking to is Jack Dennis, who is a very well-known person in the area of parallel computers. Also Jack was very interested in the design of Clue and sat in on many of our design meetings. Okay, so why do a programming language? I actually had a very well thought out rationale for why this work was important. And these were the main points. First of all, I believed then, and I still believe, that programming languages are how we communicate to programmers, because they think in terms of programming languages. So putting these ideas into a programming language is going to be a very important step to getting something that people could use in practice. The second point was putting it into a programming language and then forcing people to write their programs in that language without any cheating would show you whether the idea was really working or not. So that was a very important point. The third thing was, this was a way of making sure the definition was precise. So I felt that, in fact, the major problem with all those papers and why people couldn't understand them was because they were so hand-wavy, that in the end you didn't know what the definitions were, and that's why people had trouble pulling it out and applying it to something else. Now, programming languages, mind you, were not so precisely defined then. In fact, they're not so precisely defined now. A very common story in those days was you'd write a reference manual, it'd be a little ambiguous, the person would come along, write the first compiler, they wouldn't even notice there was an ambiguity, they would just resolve it. And then the second compiler would come along, it would resolve the ambiguity in a different way. Then there'd be a big fight, what was the right definition? Okay, nevertheless, a programming language is a mathematical object. It's a lot more precise than just writing a paper with a bunch of English words in it. And then finally, you can't ignore performance, even though it's greatly overestimated. Its importance is greatly overestimated by most of us, because all you ever need is good enough performance. You don't need the best possible performance. But when you're building a platform, and a programming language is a platform, performance does assume a great deal of importance, because everything that runs on that platform is going to be affected by what you did. So those were the 4 things I wanted to look at through the medium of designing a programming language. We also had a bunch of goals for the design. And the first 4 goals are interesting because these are the goals whenever you design any module in any system. Okay, this is what you're always doing. You're trying to define an interface. And the first question is, does it have enough expressive power so that the users of this module can do what they need to do? Okay. The second question is it simple enough that they can actually understand what they're using? The third question is, does it have adequate performance for their needs? And the fourth one is it easy to use, or is it in fact a big pain in the neck? And I use these ideas over and over again. I mean, I use them in Clue, but I use them every system I design. These things come into play. In addition, we had some specific goals for Clue. By minimality, I meant let's not put stuff into the language that isn't focused on the idea of what is an abstract data type. By uniformity, I meant I'd like to be able to do with the abstract things everything I can do with what's built into the language. And by safety, I meant let's get as many errors as possible, either automatically through the compiler or through runtime checking, so that programmers don't have to worry about finding those errors themselves. Now, fairly early in the design process, I made some restrictions. So no go-tos were out from day one, because I actually believed what Dijkstra had said, and I wasn't about to pay any attention to them. Concurrency was harder. In fact, Jack Dennis, I mentioned before, is a big fan of concurrent programming, and there was a period of time in the beginning when we thought that Clue might be concurrent. But I threw that out pretty early on fortunately, because today still people don't know what the right concurrency control constructs are. And it really was at odds with my goal of minimality. It was not germane to understand basically what data types were all about. And then no inheritance, as I said to you before, because I also thought that was sort of a red herring. And then finally, here's a bunch of other important, fairly early decisions. It's not that we didn't have arguments about these, it's just that they were decided pretty early. And these were actually unusual decisions at the time. I mean, the fact that it was a heap-based language was unusual from an academic perspective, because at that point in time, the academic programming language community thought pointers are bad, heaps are bad, etc. I came from Lisp, however, and I was perfectly happy with pointers, and I thought that was the way to go. And this turned out to be a very important decision. And the reason is simple, and actually the group at Carnegie Mellon who was doing an alternative design made the opposite decision. They tried to put everything on the stack. The reason is you want to have separate compilation. You want to be able to compile a program that uses a data type separately from the program that implements the data type. In fact, maybe even before that program has been written. This means that when you compile a program that uses the data type, you don't actually know how big the objects are. If you have to allocate space for them on the stack, you have trouble. If you can put them in the heap, then you know exactly what to do. You just need room for a pointer. So no block structure, none of that global variable stuff is what I'm talking about. Separate compilation I already mentioned. And then the final thing was static type checking. And in a way, what you can see here is the first three are Lisp. This is how Lisp was then, Lisp still is. The fourth one was a reaction to Lisp. I used to find it so annoying when I was working on my PhD thesis, and I'd spend a couple hours debugging and discover that I had an error that a simple type checker could have gotten rid of. Okay, so very quickly I'm going to go through the mechanisms in CLUE. Why don't we just go on? Okay, so the first one is clusters, which is the way we implemented data abstractions. And the name of the language, CLUE, is the first three letters of cluster. Okay, and the only important thing to see on this slide is that the cluster has a header that lists the operations. So this is making the point that what matters about a data type is the operations that you use to interact with the objects. Okay, next slide. This, on the bottom of the slide, what I have here is an example of how you use a data abstraction. And what's interesting here is the $sign notation. Not because it's beautiful notation, but because it shows you what we thought data types were all about. We thought about the operations belonging to the type, whereas today in object-oriented language we think about operations belonging to the object. Okay? And this was actually something we had quite a number of discussions about when we were doing the design of CLUE. We came down on the side of the type because we thought that binary operations were important. So if you think about matrices, with our view, you could be inside the matrix type and manipulating two matrices and seeing their representations at once, which isn't something that happens naturally if you think about the operations belonging to the objects. However, I actually believe thinking of them as belonging to the objects is the right solution. And the reason is, I don't think binary operations matter that much, but the ability to have two matrices with different implementations in the same code, that is important. It's enabled by the other point of view. Okay, what I'm showing you here is how we defined the structures that implemented the abstract type. We did this through a type definition, and we used the reserved word rect to say, this is the type that we use to implement the objects of the abstract type. Here it's very simple. I'm implementing a set of integers with an array of integers. Typically there'll be more fields. And so this is like the instance variables. This is a cluster that has one instance variable. More generally, we'd use a record that's like having multiple instance variables. Okay, and then finally, I'm just showing you the implementation of a simple operation. And what's interesting here is the use of the word CBT. So what's going on is the point of view in CLUE was when you're inside the cluster, the objects belong to the rep type. So we're talking about an array inside there. But when you go out, the type of the object changes into the abstract type. And the word CBT stands for that change. It's like Jim Morris's seal, if you think about it. Objects go out, they sort of become opaque, And you can also use CBT in the header as an argument type, and that represents they open up as they come back in, and you can see their representation. However, we did not implement them with anything like encryption. In fact, it's all done with compile time checking. So it just is a statement about a change in point of view.